Good afternoon, everyone. Good lunchtime, everybody. Good morning, everybody. Whatever suits your fancy. Welcome to another TACO-sponsored webinar. We are going to sit tight for another minute, let some more people log in, and then we will begin. So bear with us. All right, let's get going. Good afternoon again. Hi, my name is Brett Zerba, and I am an applications engineer with TACO, and thank you for attending. Today's webinar is the third in our series. Is it our third or fourth in our series for our TACO University classes? Today's is on expansion tanks, selection and sizing. It's quite a involved presentation. So it lends itself to a lot of questions, and hopefully it'll clear up some open items that may be in some folks' minds out there. So let's get prepared for that. So before we get started, let's go through our housekeeping. If you could raise your hands if you can hear me and see Rich's screen. Great. I see Derek's raising his hand, and Isaac, and many others. So that's great. Perfect. Rich Medeiros, Senior Systems Engineer at TACO, amongst other things, will be doing most of the presenting today, and I'll be moderating and watching the questions and bringing them up in front of Rich or answering them directly, however we can get them answered for you. So that's what we're going to do. So let's see. TACO headquarters in Cranston, Rhode Island. I think everybody hopes that. Here's a test question. What does TACO stand for? Thermal Appliance Company, started in 1920, 100 years ago, currently led by Johnny White Jr., third generation of the White family, and his senior leadership team is led by Cheryl Merchant, and Johnny, and the rest do a great job, and we are glad to have them running the show. Let's see what else. So this is a 6-series webinar series, and you will get an email at the end with a link to your 6 PDH hour credits. If you have some issues with any of that, just send an email in, and the team will work with you to help you out as the best we can. Other than that, I think we are all set to go. Rich, take it away.
Thank you, Brett, for that introduction. My name is Rich Medeiros. As Brett said, I'm one of the senior systems engineers at TACO. My background is mechanical engineering, and I specialize in the engineering design of HVAC systems for commercial, industrial, and institutional buildings. I am a PE, and I have been on the consulting side of the industry for most of my career. So that gives you a quick snapshot as to who I am. So today's discussion is all about expansion tanks. It's a fairly short presentation, but it does cover most of the things that are important when it comes to understanding expansion tanks and how to size and select them. Okay, so getting right into it, let me just do one more housekeeping thing here on my control panel. So expansion tanks, we're going to talk a little bit about the types of expansion tanks, expansion tank sizing, expansion tank selection, and what happens if we change the location of an expansion tank in a building, and then questions at the end. So what about the types of expansion tanks? Well, I have some narrative data, but I will go to some photographs in a moment, so don't worry so much about the narrative data, but I like to just list them here. The first type is called a plain steel tank. The second type is called a bladder style tank, and that's generally into two major categories. They're either classified as full acceptance bladder style tanks or partial acceptance. And I will talk about the difference between the two in a moment. And then the last category is called a diaphragm style tank, and diaphragm style tanks are typically partial acceptance tanks. Okay, so as the name implies, the first category is called a plain steel tank. And again, as the name implies, it's nothing more than a steel container. It typically has 4 connection points. Let me just get my pen ready here. And those 4 connection points include 2 connection points on the side here. Typically, when it comes to plain steel expansion tanks, they're mounted horizontally and not vertically. And this is where you would put a sight glass. A sight glass is, as the name implies, is a glass tube connected to the top and the bottom, and it shows you the water level that's inside the tank. Then we have 2 connections at the bottom of the tank. One is typically a valve connection that goes to some kind of drain or blowdown, and the other one connects to the system itself. So that's pretty much all there is to a plain steel tank. We don't spend a lot of time on plain steel tanks because most systems that are designed today utilize bladder style tanks. We do see occasionally a new design that uses a plain steel tank, extremely rare. And when someone is proposing a plain steel tank in a new design, we generally suggest they consider a bladder style tank. The other reason for manufacturing plain steel tanks is because there are lots of older systems that use plain steel tanks, and people buy them as replacements. They don't want to change any of the system parameters. They just want to buy a plain steel tank to replace an existing tank. So before I go on to the next group of tanks, Brett, do we have any questions floating out there?
Actually, we do have one question. What it's pretty basic, but it's important to get it answered. What's the purpose of an expansion tank? Why do we put them in systems?
That's an excellent question. So whenever you have a closed loop
on, Rich. Hold on. I apologize. We've gotten a couple of comments / questions that people are having trouble with sound. Two people. Can everyone, if you're having, not many are having problems with sound. I'm not sure what it is. I can listen fine. I have 3 people. My audio is cutting in and out. Not sure if I'm the only one. Now sound is back. I know for me it's been fine during Rich's talk, so I'm not sure exactly what's going on. Maybe the webinar is having something, but anyways, we're going to continue. Keep going, Rich. Sorry about that.
Okay, so did we answer? We haven't answered the question as to
No,
why.
we did not. We did not. I'm sorry. You're right.
Okay. So why do we have expansion tanks? Well, typically when we're talking about a hydronic system, piping system, if it's closed loop system, it's not open to the atmosphere, and it's a pressurized system. As the fluid increases in temperature, the fluid will expand. If there's no place for the fluid to expand to, then it will break the components in the system. It'll either, if there's a safety relief valve, it'll set off the safety relief valve. If someone inadvertently did not put in a safety relief valve, heating up the fluid as it expands, it will actually break components. It could break a pump, it could break pipe, it could break equipment. So you only need a small temperature change for the fluid to expand, and without safety relief valves, it would be a real disaster. Hopefully that answers the question.
Great job. Thank you.
So, and maybe I should have answered the second half of that question. So the expansion tank is a device that allows the fluid in the system to expand without destroying other components in the system. We'll get into that in a little more detail. Okay, the second category of expansion tanks are known as full acceptance bladder style tanks. And I have some red ones here, and on the right side of the screen, I have a cutaway view of a bladder style full acceptance tank. And if you'll notice, I grab my pen here. This black rubber object, that's called the bladder. The steel container, as I'm pointing to here, that's the shell of the expansion tank. There's an air gap between the inside of the steel container and the outside of the bladder. And that is an air space and where we can actually add air, compressed air, to the expansion tank. We'll talk about that in a minute. Now, at the top of the expansion tank over here, there is a round collar that protects the Schrader valve. And the Schrader valve is the device that allows us to add compressed air to the tank. And again, the air is added to the space or the void between the outside of the bladder and the inside of the steel container. And because this bladder can expand to the full volume of the steel container, so for example, let's just make an assumption that the steel container is 200 gallons. We could actually put in a full acceptance bladder, we could actually put 200 gallons of water. The water goes inside the bladder, and we could put 200, the bladder would expand to the full physical volume of the steel container. And because it's considered to be a full acceptance, the bladder would be intact. It would not destroy itself. So that's what's known as a full acceptance bladder style tank. Any questions about that, Brett?
I'm sorry, I was muted. Hold on. Actually, we still have a couple of hanging that came in about the plain steel tanks. Two are primarily the same. What is the primary reason PSS or plain steel tanks are not used? Why bladder tanks are now preferred? When did the shift occur? Because they do work.
Bladder style tanks typically are physically smaller than plain steel tanks. So when we get into the concept of, and I know I haven't mentioned the word yet, it's called pre-charge. That's when you add compressed air to the void space in the tank. So you can actually pre-charge an expansion tank, and we'll talk about what that means in more detail. When it comes to a plain steel tank, you cannot pre-charge the tank, so it starts at atmospheric pressure. And when you start at atmospheric pressure, you need physically a larger tank in order to accommodate the expansion and the pressures that you're trying to achieve. And you'll see that in a few minutes. Any other questions, Brett?
Good stuff. Yes. What happens with the air in a plain steel tank?
So the air in the plain steel tank compresses, but over time, the air can be absorbed by the water, so that the reason that the plain steel tank has a blowdown is that periodically, as you look at the sight glass, the tank eventually the water level will keep increasing because the air goes into solution. And so you have to blow down the tank slightly, add some more air to it so that it does its expansion and it doesn't get waterlogged.
Excellent. Thank you.
And along with that, I should mention that because the bladder style tank, the water is inside the bladder and the air is between the outside of the bladder and the steel container or that void space, that means that the air and the water do not mix in a bladder style tank. So the air does not come in contact with the water. Okay. Continuing right along, as they say. The next style is called a partial acceptance tank. And in this case, again, you look at the cutaway, you can see that the bladder in this case is physically smaller than the one in the previous picture. And in a partial acceptance tank, the bladder does not have the same physical volume that the steel container is. So in our example a moment ago, we said that the steel container, let's say in this case, it's still 200 gallons. The steel container is 200 gallons, then the bladder can only accept a portion of that, and that's where the term partial acceptance comes from. So maybe the bladder, and I'm just going to make up a number, so maybe the bladder can only hold 60 gallons in this case instead of the 200 gallons. So if for some reason you try to put the full steel container volume inside the bladder and try to fill the bladder up to 200 gallons, since the bladder is limited to 60 gallons in our example here, then the bladder can rupture or compromise, could create a leak. So a partial acceptance bladder can never expand to the full volume of the steel container. Okay, moving right along, as they say. The next category is called a diaphragm style tank. And in this case, rather than having a bladder, we have a diaphragm that resembles a little bit like a rubber bowl. You can see it's open at the top here and it's closed at the bottom. The water enters the bottom of the tank and the air enters the top of the tank. And again, it's considered to be partial acceptance because the bladder can only accept a small percentage of the total volume, similar to the one I showed you previously. Again, perhaps the tank has a physical steel container volume of 200 gallons, but the partial acceptance maybe is 50 gallons in this case, because it's a diaphragm style tank. So those are the three basic categories of bladder style and diaphragm style tanks. Before we go into sizing these tanks, any questions about what we've covered so far?
Yeah. Which ones do you recommend, or how do you decide which one to use?
Well, as it turns out that a bladder style tank, the most expensive bladder style tank is the full acceptance bladder style. And then the second most expensive is the partial acceptance bladder style, and the least expensive is the partial acceptance diaphragm. In the first two bladder style tanks, those particular ones that I showed you have a serviceable bladder. You can physically take the bladder out and replace it with a new bladder. When it comes to a diaphragm style tank, if the bladder should rupture or be compromised in any way, you cannot replace the diaphragm. So you'd have to discard the tank. So generally speaking, when people are looking to save money in first cost, they go with a diaphragm style tank because it's the least expensive. I personally prefer the full acceptance bladder style tank with the replaceable bladder. They're somewhat idiot proof in the sense that if they do expand to they fill up with water, the bladder, it's not going to rupture because it holds the same volume as a steel container. If you have a partial acceptance, whether it's a bladder or a diaphragm style, you run the risk of rupturing the bladder. So it becomes a choice of serviceability, cost, and those are the two major issues. So the more serviceable, the full acceptance bladder style is more expensive. The least expensive is the diaphragm style tank. And in a competitive market, we provide the diaphragm style tanks because in some cases that's what people are interested in purchasing.
Good stuff. Size might have something to do with it, or quantities and size as well, but yep, good stuff.
Okay. So let's talk a little bit about expansion tank sizing, and there are 6 things that we need to understand before we can do an actual tank sizing. The first thing is we need to know what the minimum or fill pressure is, the maximum pressure. The third thing is the minimum temperature, sometimes referred to as the fill temperature. The maximum temperature, sometimes refers as to the system operating temperature. And then the fluid type, and then finally the system volume in gallons. So in all of our values, by the way, today we're using the US units or imperial units. When we get into the selection of the tank, you'll see why we did it that way. Okay. So let's look at a specific example. Given a 75-foot tall sample office building, let's find the expansion tank size. So let's go into a diagram here that demonstrates a very simple office building. And in our case, the mechanical room is at the lowest level inside the building. And our piping system is going to go from the lowest level to the highest level. Essentially, the piping system is going to be as high as the height of the building inside, which in this case is 75 feet. So I am going to draw a simple little pipe. If I can grab my pen here. Let's assume that our piping system goes from the lowest level of the building and rises vertically upward to the highest part of the building. And let's say that I add water, fill that piping system with water. So let's just put a little connection here. And at the top, let's say I put in a very simple valve here. And I keep that valve, initially I keep that valve open, and I put a bucket. Today I'm going to use a plastic bucket from Lowe's. Yesterday or the other day I used one from Home Depot. So if I fill water in this piping system, it fills it from the top, from the very bottom to the very top, all the air comes out. I get a couple of drops of water out and I stop filling it. At that point, I close this valve at the top. Now my piping system is 100% filled with water. If I put a pressure gauge at the top, and for a moment I put a pressure gauge at the bottom, let's talk a little bit about what the pressure would be at the bottom of this piping system. If I had a little pressure gauge, turns out that the pressure inside there would be equal to the height of the building converted into pounds per square inch. So the conversion from feet of water column, so it's put that in here so you can see what that is, 2.31 feet of water column is equal to 1 pound per square inch, PSI. So if I know what the height of the building is, the building is 75 feet tall, I divide that by 2.31 and I discover that the pressure at the bottom of the building is around 32, I'm going to round it off, about 32.5 pounds. 32.5. So does someone want to type into the question area or the chat area, wherever that actually winds up being? If I have for the static height of the building 75 feet, and I've just calculated what the pressure is, does anybody know what the pressure is at the top of the building in pounds per square inch gauge? PSIG.
Someone said 0.
Zero is correct.
14.7, 0.
0 pounds per square inch gauge, but we don't want 0 pounds per square inch gauge. We want something higher than that, because if we had 0 pounds, we'd have no way of forcing the air out of the piping system at the top of the building. So what we'd like to do is increase the pressure so that at the top of the building we had somewhere between 5 pounds and 10 pounds, somewhere between 5 and 10. And because today I want the numbers to come out even, I've selected 7.5 pounds at the top of the building. So I want 7.5 pounds per square inch gauge at the top of the building. If I put 7.5 pounds at the top, I have to add that pressure to the bottom. So the pressure at the bottom is now going to read, point to it, 40 pounds per square inch gauge. Now, this is a very important concept. As simple as it might seem, it's a very important concept in terms of how we figure out what the pressure needs to be in the piping system, which is at the bottom of the building. It's called the minimum pressure or the fill pressure. Anybody have any questions about how we arrived at that?
Nothing posted.
Okay. So we're going to repeat what we just talked about in a narrative format here. Before we do that, let's take a quick look at the mechanical room. So in our mechanical room, which we said originally was in the bottom or the base, I'm sorry, the first floor of the building. And here's where we're going to have the expansion tank. expansion tank is going to be connected to the piping system on the suction side of the pump. There we are on the suction side of the pump. This is called a fill valve over here. And we're assuming that all of this equipment is at the lowest level in the building for our discussion. And there's our expansion tank. We just figured out what the minimum or fill pressure needs to be. So let's just repeat that one more time. The minimum pressure is equal to the height of the building converted into pounds per square inch gauge, which in our case was 75 feet divided by 2.31 feet per pound per square inch gauge is equal to 32.5 pounds per square inch, and that would be at the bottom of the building. We know we want somewhere between 5 to 10 pounds of pressure at the highest point. I decided to use 7.5. So 7.5 plus 32.5 is 40 pounds. And again, that's called the minimum or fill pressure, as we've indicated here on this little diagram. Now, it's very important to recognize that most manufacturers, including Taco, when we ship our expansion tanks, we pre-charge them to 12 pounds, 12 PSIG. That means that the space or the void between the bladder and the steel container on the air side is pre-charged to 12 pounds. In this system, the tank needs to be pre-charged to 40 pounds. So that means that when the expansion tank arrives physically on the project site, we need to add compressed air to pre-charge the air side of the tank to 40 pounds before we connect it to the piping system. Now that's extremely important. You do not connect the expansion tank to the piping system and then pre-charge it. What you do is you pre-charge the tank to 40 pounds and then connect it to the system. Any questions about pre-charging the tank?
Nothing's posted there. The 40 PSI that you referenced, the minimum pressure, that's a calculated value, correct?
Correct.
People are asking how to add additional pressure to the system. So it's kind of getting a little confusing for some, I guess.
Yeah, so while we're chatting here, if someone, maybe if they would like to unmute themselves, the person that's asking that specific question, and then we can try to answer their question, get a little bit more detail as to what they're trying to.
I'll try unmuting. They can't. We can do. How would you get the additional pressure at the top of the building? Is what Thomas asked. I can try to unmute them. I don't know if I can.
Oh, okay. You do that with the fill valve. So over here on the left side, I think I understand the question now, Brett.
Yeah.
So over here, the minimum pressure or the fill pressure is going to be the same as the tank pre-charge pressure as it is the fill pressure at the pressure regulating valve. So you have typically you have a pressure regulating valve. In this case, the pressure regulating valve is connected to the same pipe that the expansion tank is, and they're all at the same elevation. So you would pre-charge the system to 40 pounds by setting the pressure on the pressure regulating valve to 40 pounds, 40 PSIG. And then you would have, in our case, you would have 7.5 pounds at the top of the building. So it's with the fill valve that you regulate the initial pressure. Does that answer their question?
I'm sure it does. Yes, it does. He responded. Here's another question. Is it not necessary to account for piping losses for fill pressure?
That's correct. This is all static pressure. It does not have anything to do with the fluid flowing in the system. And we'll talk about the fluid flowing in a minute, but initially for setting the pre-charge and the fill pressure is under static conditions. There's no water flowing.
Good stuff. Good stuff.
Okay. Let's move along, as they say. So we've already figured out what we need for the minimum or fill pressure. The next thing we need to know is what the maximum pressure is. And this is a little bit more involved. In the maximum pressure, again, all of our equipment in this example is at the lowest level of the building. And in this case, the pressure is 40 psig. But what would the maximum pressure be? Well, let's assume for a moment that we had a piece of equipment at this elevation, and that piece of equipment had a maximum design operating pressure of 150 pounds per square inch. We would not want this equipment at this elevation to ever see that 150 pounds. So typically we'd put in a safety relief valve, and most people will set the safety relief valve at about 10% below the maximum pressure in the system. You can go less than that, but 10% is a reasonable value. So in other words, if the pressure for the equipment is 150 pounds, 10% of that is 15. So 150 minus 15 would be 135. So we want to set the safety relief valve at 135 pounds per square inch gauge. Now, pressure relief valves are very, very simple devices. They're basically a disc held closed by a spring that can be adjusted, and that's how you get the adjustment, in this case, to 135 pounds. But the pressure in the piping system should be less than that, because if it approaches 135 pounds in the piping system, then we run the risk that the safety relief valve will begin to leak or drip. Sometimes we refer to it as weeping. So I want the pressure in the piping system to be a little bit less than that, so I don't have a nuisance leak. So I'm going to make the piping system pressure 130 pounds, 5 pounds less. So again, if I have 5 pounds, 130 pounds PSI, sorry, that's supposed to be a PSIG. If I have 130 in the piping system and the safety relief valve is set at 135, I'm going to be below my equipment rating, below the rating of the relief valve setting, and so I'm going to shoot for 130 here. Now, when the pump is running, the pump can add pressure to the discharge side of this pump. And generally speaking, the maximum pressure or close to the maximum pressure that the pump can add to the system is when there's zero flow. So if I put a valve over here and I close that valve and I put another valve over here and I close that valve, there would be zero flow. If the pump is running at full speed, then the pump would produce a pressure differential. So whatever that pressure differential is, let's assume it's 20 pounds in our case. If the pump can produce a 20-pound pressure differential, then that means that the suction pressure in the pump, if I take 130 minus 20, wants to be 110 pounds. So let me go through that again. If I have 110 pounds at the suction, if the pump adds 20, add 20 to that, that would be equal to 130. 130 is less than the relief valve, which is definitely less than the equipment rating. So the maximum pressure I want on the suction side of the pump, which also happens to be the maximum pressure that I want at the expansion tank, in this example is 110 pounds. Any questions about that?
Actually, a couple of questions still hanging out there. This is a good question. This is probably one of the better ones. What happens to the expansion tank if you don't pre-charge it before connection to the system?
That's an excellent question. So if you don't pre-charge the tank, let's assume again the tank came from the factory with the pre-charge of 12 pounds, but the fill pressure was set at 40 pounds. If you connected the tank to the system and the tank is only pre-charged to 12 pounds, then the bladder will start filling up with water. And I don't know exactly unless I did the calculation, but let's assume for a moment that the bladder filled up 50% of its capacity. So let's assume for a moment that the tank had roughly 100-gallon capacity. If I didn't pre-charge the tank and I connected to the system and the pressures equalized, the only way the pressure could equalize is if it started filling with water, and maybe it took 50 gallons to fill the tank. Well, if the tank is half full with water, then when the water starts expanding as a function of temperature, it may not have enough space left in the tank to expand without exceeding the maximum pressure that you've selected.
Rich?
Yes.
Okay, I thought I lost you. You scared me.
Does that answer the question?
Yeah. And
Okay.
the value 20, you just pulled that out of the air, but that, where would you actually get that value?
So when you're looking at a pump curve, it generally is when you have a zero flow. It's sometimes referred to as the shutoff head of the pump. So wherever the pump curve intersects the vertical axis at zero flow, that's the shutoff head. And that's how much pressure that, generally speaking, is pretty close to the maximum pressure that the pump can produce, is at zero flow. So you get that from the pump curve.
Okay, pump curve. And then, so you said that you needed to add water, or excuse me, the pressure regulating valve. What if the domestic water static pressure is not high enough for the proper fill pressure?
Well, in that case, you would have to install a booster pump system. In order to fill the piping system, you'd have to take, for example, if your water pressure came from the street or the city water supply, and it would had a maximum pressure of, say, 30 pounds, and you needed 40 pounds, you'd have to have a booster pump system in order to increase the system pressure to accommodate not only typically your HVAC system, but also your plumbing system.
Excellent.
Okay, so now we're going to erase all this stuff and recap what we just did. Remember, we want 150 pounds maximum at the equipment. Therefore, we want the safety relief valve at 135. We want a little bit less than that in the piping system. So we want the pressure in the piping system to be about 130. If the pressure developed by the pump is 20 pounds, in this case, 20 PSI across the pump, which is equal to 46.2 feet at shutoff head. That means we want the suction pressure to be 130 minus 20, which is 110. And that is also the pressure we want at the maximum at the expansion tank. Just recapping what we just covered. Okay.
Good.
Exciting stuff. So now we know the minimum pressure, we know the maximum pressure. The next thing we need to know is what is the minimum temperature? Typically, the minimum temperature or the fill temperature is the temperature of the water that comes in from your municipal water supply or your well system. If you happen to be in New England, that temperature is usually around 50 degrees Fahrenheit, but it depends on where you are in the world. Your groundwater temperature could be higher than that. There are places in the Middle East where I know that the groundwater temperature is up around 70 to 80 degrees. So that could potentially be your fill water temperature or minimum temperature. We do know that in Alaska, we've spoken to the guys up in Alaska, and the water temperature below grade is somewhere around 40 degrees Fahrenheit. So it depends on where you're getting your water from, but typically for most places, it's somewhere between 40 and 60 degrees Fahrenheit. The maximum temperature is whatever your system design is. And in our case, we're going to assume that it's a hot water heating system, and our maximum design temperature is 180 degrees. Now we have 4 out of the 6 things we need. The next thing is we have to make sure of the fluid that's in our system. And in our case, we're going to assume that the fluid type is water. And the last thing we need to know is what's the total volume of water in the system. And that, in our case, we're estimating it to be 2,000 gallons. Okay, now that we have this information, let's go live to TACO's website. And
Rich, as you're getting to the website, here's a comment/question. Determining system volume on large systems is so tedious. Do you have to account for every foot of pipe? Is there a scale back assumption that can be made? That's the $64,000 question, right?
It really is. And in fact, today, in today's environment, we can use software to lay out the piping system. And one of the software packages, I don't know if you've seen it demonstrated yet, that Brett is going to be demonstrating, I think next week, is it, Brett?
I believe so.
It's called the HSS, or HVAC System Solution software. And if you use that software carefully, it will actually calculate the total volume of water in the system for you. But yes, it is manually, it's a very tedious process. We recommend that you try to use some software application so you don't have to get through that. But you do have to account for every length of pipe in the system in order to calculate the correct volume of water.
We have a couple of questions about location. You want to answer them now, or do you want to wait?
Well, yeah, let's ask the question. I may defer the answer, but let me just make sure we have the question on the table.
Yep. In a chilled water system, where should the expansion tank be located relative to the chiller and air separator, and where relative to the highest and lowest point of the building?
Well, let's answer the first part. And the first part is the expansion tank should always be connected to the suction side of the pump. That's known as the point of no pressure change. As far as where it should be located, whether it's the lowest part of the building or the highest part, we're going to get into that in a little more detail a little bit later on. So if we could hold off on answering the second half of that question. The first half is the expansion tank should always be connected to the suction side of the pump.
And this question comes up pretty common. You're talking about a heating system. What would your maximum water temperature you recommend on a chilled water system?
Well, the chilled water system, I generally select the maximum water temperature of 110 degrees. And the logic there is that even though during operating conditions, perhaps the water temperature might be as low as 45 and as high as, say, 55, or maybe in some cases a little higher than that, maybe 60 degrees. However, when you fill a piping system with water and you fill it at the street temperature of, say, 50 degrees Fahrenheit, but if the chillers aren't started, then it's possible that the water would sit in the building. And we just went through a period, God, it seemed like forever. We just had a change in weather here in New England. And the temperatures for the last 3 or 4 weeks were ridiculously high for us. In some cases, they went over 100 degrees. So if you imagine for a moment you have a chilled water system that was filled initially with, say, 50 degree street water, but then it sat in the building before the chillers were started, and the temperature just got up to ambient temperature of 100 degrees or even warmer, the water will expand, and if it doesn't have any place to go, it'll set off the relief valve. So I generally pick 110 degrees as the maximum water temperature when I'm doing a chilled water system.
Good stuff. One last one. On a primary, secondary pumping system, which side of the system should the expansion tank be installed on?
I always like to install the expansion tank on the primary side of the system. You should not put an expansion tank on both sides of the system. You should only put it on one side, and I recommend putting it on the primary side.
Awesome.
Okay, so we are at the Taco Comfort Solutions homepage. On the left-hand side, about halfway down, it says Apps. I'm going to click on that. Let me go back to the homepage. I clicked on that private. So on the left-hand side, about halfway down, it says Apps, and then it says Expansion Tank on the drop-down menu on the right. Click on that. And then we wind up with the input for our, let me zoom in a little bit. So we're going to start off with water. I'm going to leave the piping material at copper for a moment. System volume, remember that was 2,000 gallons. I put that in at 2,000. The fill temperature was 50 degrees Fahrenheit. The maximum temperature in my case was 180. The fill pressure is 40 pounds. The maximum pressure is 110. And then I'm going to scroll down, click on search. Before I look at the selections, I'm going to point out something here. The software has calculated the system expansion. And in this case, it's approximately 53 gallons, a little bit more than 53 gallons. We're going to ignore plain steel tanks for a moment and just focus on bladder style tanks. In a bladder style tank, we need a steel container that's approximately 95 gallons or greater. So now we look at what the software has selected. Go over here and erase that. We'll look at what the software has selected, zoom out. You can see the first tank that it selected says that the steel container is 119 gallons. Bear with me 1 second. These pens make me crazy, Brett. Okay, the steel container is 119 gallons. Well, that's greater than the 95 that minimum that we need, so that's good. And look at the acceptance volume. The acceptance volume in this case is 119. And since the acceptance volume is equal to the steel container volume, that's called a full acceptance tank. That means, again, that the bladder can expand to the full physical volume of the steel container. And the acceptance volume has to be equal to or greater than the expansion volume. In our case, the expansion is just over 53 gallons. In this case, it's 120, roughly 119 rather. And so it meets that criteria. So that first tank, that will do the job. The second selection, again, the steel container is 112. It's greater than 95, so it meets that criteria. The acceptance volume is 61 gallons. In this case, the acceptance volume is less than, I can do this properly, than the tank volume. If that's the case, then this is a partial acceptance tank. And since it meets the expansion, 61 gallons is greater than the expanded fluid, it meets that criteria, and so this tank will also do the job. I'm going to skip over the next one and go over to the fourth one down. In this case, the steel container is only 57 gallons, so it's not large enough. However, they're recommending 2 of these tanks. So 2 times 57 would be 114. That's greater than the 95. And the 27 times 2 is 54, which is greater than the 53. So this tank would also do the job. And for today, I'm ignoring the plain steel tanks. I will point out, though, look at the size of the plain steel tank. Needs to be 400 gallons because the plain steel tank has a minimum volume requirement of 354 gallons. So whenever you talk about a plain steel tank, it's always dramatically larger than a bladder style tank. Any questions about the selection software and how we arrived at these different size tanks and bladder sizes?
Actually, it's probably a basic question, but it's good to bring it up. Why is the pipe material specified in the selection software?
So in this case, we have 2 piping materials that we can choose from, either copper or steel. If it's copper, copper expands at a greater rate than steel does. So as the copper heats up, it will accept a very tiny percentage more of the system volume than steel will. In other words, we'll take a little credit for the pipe expanding. So if you'll notice down here, it's calculated the system expansion is 53.44 gallons. If I change that to steel, which does not expand quite as much, if you'll notice now the expansion is 55.78 instead of 53.44. That means that the steel does not expand, so we can't take credit for the expansion of the steel as much as we can for the copper. So to be conservative, if it's a small system, I generally select copper. If it's a large system, I generally select steel. So for today's selection, I decided to leave it on copper. And that's what gave me the 53.44 gallons.
Good answer.
Okay, I have a couple of other things I want to share with you, but before I do that, do we have any other questions out there, Brett?
Somebody asked about plastic pipe. but
Well, depending on the system, I was just reviewing a geothermal system a little bit earlier today. A plastic will actually expand a little bit more than copper. And depending on how much plastic there is in the system, some engineers will actually design a geothermal system using plastic pipe and not install an expansion tank because the plastic will expand enough to accept the volume of expansion of the fluid as the temperature increases. But I always recommend, whether using plastic or steel or copper or some other material, to utilize an expansion tank.
if the tank has an acceptance volume that meets the requirement, why the tank volume requirement?
The reason for the tank volume is because as the fluid expands, it compresses the fluid in, it compresses the air. Let me go over here. Let me know if you can see my whiteboard, Brett.
Yes, I can.
So I'm
It's
going to try
blue
to
and white right now. Oh, it's just white now.
Okay, so here, let's take a look at this. Let's assume for a moment that we have a steel container, and that steel container has an empty volume, empty physical volume of, let's say it's 300 gallons. I'm going to draw 3 tanks here. There's nothing in this tank but air, and it's sealed, let's say. So far, so good?
Yep.
Let's assume that the pressure inside this tank, before we do anything at all, is I'm just going to arbitrarily make that pressure 10 pounds per square inch, 10 psig. PSIG. It's 300 gallons. I'm now going to draw, let's put the word gallons up here so I don't lose track. Now I'm going to draw another tank exactly the same, only it's has 100 gallons, which is 1/3 of the tank. Let's say it has 100 gallons of water. All right. If it has 100 gallons of water, let's assume it's at the same pressure as my first tank. It's still at 10 pounds. In other words, I had a valve at the top of each tank. And in the first one, I closed the valve and I pressurized it to 10 pounds. In the second one, I kept the valve open until I got 100 gallons in the tank, and then I pressurized it to 10 pounds. Excuse me.
You're quite the artist, sir.
Okay. If the water down here is 100 gallons, what's the volume of the air? Anybody want to shout that out or want to take a guess?
A couple of people said 200 gallons.
200 is correct. And if I had my pressure initially at 10 pounds, PSI, that's 200 gallons. Now, let's take that same exact tank and now say it's definitely closed to the atmosphere. And now I'm going to allow the fluid to expand. And now I'm going to let it expand. So now that I have 200 gallons of water in the tank, 200 gallons. There's water. How many gallons of air do I have?
Someone said 100.
Correct. I have 100 gallons of air. Only this time, my initial pressure was 10 pounds. What's my final pressure over here? Well, it turns out that the pressure is indirectly proportional to the volume. So I had 100 gallons over here, 200 over here. So since its pressure is inversely proportional, it's 200 divided by 100 times the initial pressure. But the initial pressure has to be converted into absolute pressure. So 10 plus 14.7, because the conversion from gauge pressure to absolute pressure is 14.7 plus the gauge pressure. In our case, it's 24.7.
Good math.
So 24.7 times this ratio, well, 200 divided by 100 is 2. So that means 24.7 times 2 is equal to 49.7. I'm sorry, 49.4. PSIA. To convert that back into gauge pressure, I need to subtract 14.7, which in our case, of course, is going to be, 14, not 17, 14.7. In our case, what do I do? No, I got it okay. There's the decimal point right there. In our case, of course, 14.7 is going to bring it back to 34.7. Did I do my arithmetic correct? Let's try that again.
Looks it.
14.7 plus 10 is 24.7 times 2 is 49.4 minus 14.7. My new pressure is going to be 34.7. 34.7 pounds per square inch gauge. Now, if my original tank was not 300 gallons, let's say it was 250 gallons, and then if I went from 100 gallons to 200 gallons, then my airspace would go from 150 to 50. And now my ratio would be 3 to 1. So my pressure would be 3 times as great. So the steel container regulates the pressure at the high pressure. The smaller the steel container, the higher pressure is going to be. Kind of a long-winded way to answer the question, but it's an important concept. We're on the home stretch, Brett. Any questions?
Yep. Few minutes left. A couple more about location, or one good one, one that's been hanging out there about location. So if you want to talk about where to locate it, or up high, I can read it. Remember the other question too. In the chilled water system, where should the expansion tank be located relative to the chiller and air separator, and where relative? Oh wait, that's the same question. To the highest point of the building. One gentleman had a 340-foot tall building. Where the hell did that question go? I lost it.
Well, let me answer the question
Yeah.
directly then while you're looking for the question. If you change the physical location of the expansion tank, let's say in our case, we moved it from the bottom of the building to the top of the building. Well, if we moved it to the top of the building, the pressure we set at the top of the building in order to maintain a minimum of 40 at the bottom, then that would be that 7.5 pounds. So instead of using 40 pounds as the minimum pressure, I'm going to have 7.5 pounds. And then at the bottom of the building, I'm going to have, instead of 110 for a maximum, it's 110 minus the 32.5, which is 77.5. And now if I do a quick search here, you'll notice the expansion is still 53.44 gallons, but now the tank physically is only 70 gallons instead of 95 gallons. So whenever you move the tank from the lowest part of the building to the highest part of the building, the tank gets physically smaller. So that's one of the advantages of moving the expansion tank from the lowest elevation to the highest elevation. The tank becomes physically smaller. Now, that may not make any sense in terms of if it's a very large building and say the tank happens to be 1,000 gallons, and even if it went to 70% of that, 700 gallons, that's still a lot of weight. At roughly 8.33 pounds per gallon times 700, that means that's around 6,000 pounds. So you'd have to accommodate that additional weight at the top of the building in the structure somewhere.
So here's the other question about that. That's a great answer though. That weight, I guess sometimes people overlook that or miss that great detail. Where is the best place to place the expansion tank in a system where the chillers are on the ground level and the building is 340 feet high?
Well, it depends on where the pumps are located. If the pumps are located at the same elevation as the chillers, the expansion tank needs to be connected to the suction side of the pump. So if the expansion tank, if the pumps are at the bottom of the building and the chiller's at the bottom of the building, the expansion tank should be at the bottom of the building.
It really has to do with where the pumps are located for the most part.
Correct. And they
Yep.
need to be connected to the suction side of the pump to be the point of no pressure change. Well, we're sort of at the end of our
Yep.
hour. Brett, do we have a last question out there before I turn it over to you?
Nope. Well, here's a question I've never seen before. Are you familiar with the method where you add a known quantity of salt to the system and circulate it for a while, then check sodium content in parts per million to determine system volume?
That's a pretty clever way of doing it. No, I haven't done it that way. I wish they could send me some like a white paper on it, and I'd be happy to review it. But that's fascinating.
The only problem is that means the system's already installed,
Yeah,
right?
which might be a
So
problem.
so what that's going to tell you the system volume, but what about that? That's good for chemicals and adding chemicals maybe to give you the exact amount, but you've already hopefully got an expansion tank installed, I would think.
Yeah, that could be a problem. If you add salt to water in a system, it could be quite corrosive. So
Yeah.
anyway, that's an interesting concept. I'd love to find a little bit more about it.
Yeah.
I
So
haven't
maybe
used that technique myself.
no, that's pretty ingenious. Lot of smart people out there, Rich. Someday maybe we'll be in that category. Who knows?
So at this point, before I turn it over to Brett, I want to thank everyone for participating in today's presentation. If you have any questions after the fact, you can always send it along to us. We'd be happy to answer them for you. Stay safe out there, and I'll turn it back to Brett. Brett, take it away.
Thanks, Rich. Great job, and quite a few people thank you for your presentation. They really appreciate it. So great job as usual, everybody. Thank you for your attention. We will look forward to seeing you next week for series number 5. I'm pretty sure it's number 5 next week. God, we're zipping along here. So be on the alert for that. Other than that, as Rich said, please stay safe out there and take care, everybody. Goodbye.